Solid form quantification, where is it important, where is it needed? One good example is the pharmaceutical industry, especially in the drug development, where active pharmaceutical ingredients, which I will call API for the next minutes, play a crucial role in drug development, so especially the physical form of this API. Why is that? Because 80% of API molecules exhibit polymorphism. That means the drug developer needs to handle a very wide range of physical and chemical properties, and these have an influence of different criteria like bioavailability or thermodynamic stability, but also things like processability. So here you can see an overview about different phases in drug development, and actually everywhere where I placed a yellow asterisk, solid form quantification is important in the one or the other way. So of course you have the normal polymorphism screening, but you also have crystallization development. You can think about formulation, early formulation, final formulation, and even in the regulated environment during polymorph purity or during production, there is the need to quantify solid API forms. So the drug developer needs to choose the best API form, and this decision is based on the development, on the formulation, and it's also important later on for production and also for storage. Now, what is the status quo? How is the drug developer handling solid form quantification? So actually, we talked to a lot of customers, and we found out that there is no universal technique available at the moment to monitor and to quantify physical API forms in solid samples. The good news is there is a toolbox of different methods that can be applied to different API forms. And these methods are, for example, powder X-ray diffraction or optical vibrational spectroscopies like Raman or infrared spectroscopy. And there's also some thermoanalytical methods like differential scanning, calorimetry, or thermogravimetric analysis. The problem here is that though all of these methods have a lot of positive aspects, they all have some general issues, some more and some less, when it comes to solid form quantification. So one is a high limit of detection or low accuracy. Other ones need extensive calibration, which is really time consuming, or sometimes a high expertise level is needed. Maybe not for the measurement, but afterwards for the analysis. And one special issue that occurs often is amorphization. So how can I quantify amorphous content? One other method that is state-of-the-art at the moment is solid-state NMR, nuclear magnetic resonance spectroscopy, where you can either directly observe fluorine or carbon signal directly, which is totally made for quantification, but takes quite a long time to measure, or you go via so-called cross-polarization, but this in the end needs a lot of calibration as it is not made for quantification in the first place. So it's not straightforward. There are some further drawbacks. So if you see we have a large footprint, if you compare this method against the other ones I just presented in the slide before, there's a high cost of ownership. It is sometimes time-consuming to run these experiments, and there is a high level of expertise needed. And as of today, there is no sample automation available. So we came to the point where we asked ourselves, is there a possibility where we can combine the analytical power of NMR with an easy-to-use solution? And we came up with the answer, which is yes, we can do this with time domain NMR in form of a benchtop system. Now, before telling you more about this solution, I would like to dive a bit into a very short introduction to NMR. Actually, this introduction is made for the non-NMR experts, and I hope I can show you a bit of what NMR means and where our signal comes from, just that you can understand how our method is working. And I promise I will not show any Hamiltonians or any other thing, because it's simply not needed here.